Hi. DHO-REMOTE is a program I wrote to make a Bode plot with the digital oscilloscope. This time I want to show that you can also use this solution. It is an impulse-based transfer function determination. You can use that also with a linear control loop to see the open loop gain. The setup for such is that you have that you need a transformer. More about it later. Again, you need a square wave signal generator to drive that, and the output of that transformer. That output of the transformer will be put in series with the feedback loop. The idea is that the signal that develops here is basically between the output and the input of the operational amplifier. I used the 741. And because of the high loop gain of this opamp, any signal that you try to put between the output and the input will develop at its output, because any signal at the input will be multiplied by the open loop gain of the opamp. And so any finite output signal will be a very tiny input signal. Now that's what we will show on the scope screen later. For now, I first want to show how you get a transformer. I have a photo of it. I have found two of those transformers in my junk bin, and I think they are audio transformers. So I think I got them long ago from ripping components from a transistor radio or something. So what I did is I just put the generator on one winding of the transformer, and the other winding I put on the oscilloscope. That was just to determine if this transformer would be suitable. So I have this setup: generator on one side, one winding, and the other winding I put a ground lead of the scope and the signal of the scope. And I terminated with 150 ohm. So I started the scope program, the DHO-REMOTE program, like this, with an IP address. Now I trigger on channel 1. The scope already displays the signals. And yeah, basically all I need to do is press Bode plot. And what you can see from here is that the first graph shows the two channels. Channel 1, the yellow one, is the input, the generator. It's a 10 kilowatt square wave. While channel 2, the blue one, that's the output of the transformer. Now it's clear that there is a big amplitude difference. And that can also be seen from the second plot in the middle. That is the FFT transform of both channel 1 and channel 2. So you can see it is a 10 kilowatt square wave. You can see that the amplitude is bigger on channel 1 compared to channel 2. And you can also see that it tapers off like this. It should taper off with 20 dB per decade like this, but there is finite bandwidth, so that's exactly what we want to see. So the last plot is basically the difference of channel 1 and channel 2. And since channel since channel 2 is smaller, you see a negative. So it is about minus 15 dB, 14.4. And 15 dB I mentioned because that's 5 times. So I assume this is a 1 to 5 transformer. I drive the input, and the output is 15 dB lower. And that's good, because that means that the input is high impedant and the output is low impedant. And the output is what we want to put in series with our scope. So I can see that the bandwidth of this this transformer, well, basically bandwidth, you can see that the loss, because it is minus 15 dB, that goes up here. So actually it is sort of resonating here. And you'll also see the phase changing from 0 degrees, and it goes up a bit to well, what is it, 30 degrees or so. But you also see some noise in here, and basically that is because, well, you can also see it here, there is some noise in the signal. And one way to set it up is to add averaging. And instead of doing that manually, I also made now a button setup scope, and that will call the auto setup of the scope. And after that, a lot of settings are being applied. So now the averaging has been enabled here. The channel bandwidth has been limited to 20 megahertz because for almost every Bode plot you don't want to have the full bandwidth. The sampling is quite high. The highest sampling rate, 1 mega samples memory depth. And if I now make a Bode plot again, you see it is less noisy than before. And that's mainly because I have now 16 time average on exactly the same signal. I can also make the time base a bit longer, because up to 100 microsecond the sample rate remains the same. So it doesn't matter what you do here. It's all, if I change it from 100 microseconds to 2 nanoseconds, the sample rate remains 625 megasamples. So if I make a new Bode plot, it will be exactly the same as this one. And you see it takes about, well, what is it? A second or two or so, and then you have the complete Bode plot. What I also plot here is the sample rate here. That's the same as what mentioned here. The maximum FFT frequency is half of the sample rate, so that is 312 megas. That is what you see in this middle chart. But this part is all noise, and it's not interesting because this transformer cannot go any further than, well, 1 megahertz is still fine, 2 megahertz, and then it starts to resonate here. So I think for the open loop gain, which I want to measure for my opamp, I think 1 megahertz should be doable. So that's why I tried this transformer. Okay, I'll rewire the things to make it resemble. Let's see, that was this one. To make this setup, because currently just the input of the transformer and the output of the transformer I'm put on the scope. So I closed the program because it needs to be started up with a command line argument minus loop gain or -L, because the inputs and outputs are slightly different defined. So now the output of the opamp will be channel 1, the big signal, and the small signal will be on channel 2. So this is how it looks like. The signal is a bit smaller than before. No, I don't want to see that. So the amplitude is apparently 180 millivolt. That doesn't really matter. It's still averaging, so the setup is the same, except you see the blue one is actually, well, it's almost constant, the signal, because that's compensated by the loop gain. And if I now make a Bode plot of this, so again, the time domain signals here are a square wave with some, looks like overshoot. Let's zoom in a bit. Yeah, there is some overshoot here, but that's all fine. That's all because during the transition something happens here. You cannot see it on scope, of course. Falling edge. Yeah, you see here some overshoot. So this contains all the information about the stability of this circuit. So the second one is again the frequency transfer. The stimulus, the output is, well, it's not the stimulus, the output of the opamp has a smooth transition up until almost 1 megahertz, and you see the feedback stays constant, and the difference is the loop gain, and that is shown in this plot. Around 10 kilohertz, the loop gain is about 37. And it goes smoothly down That's expected, right? And the opamp should be 20 dB per decade going down. And here around 730 kilohertz, the loop gain amplitude goes to 0. And at that particular moment, the phase is, it starts here at 90 degrees and it goes down to 71. So that means this is stable. As long as this is above 0, it is stable. And if it is above 45 degrees, then it is considered to be okay. If it is below 45, it could still be stable if it is at least above 0, so in between 0 and 45. But it will start to show some ringing. And that's also something that I can show, because basically what this shows is that, well, this all works fine. I can also show a bit lower, but the problem is a bit that this is for 10 kilohertz. Well, actually I can show with, I'll change the signal with 1 kilohertz. And you see it here changed gradually because of the averaging. I'll do the setup again. And basically it says here, detected the signal of 1 kilohertz and apply a frequency below 625. And below 625 is basically the complete time that the scope has captured. But for now I'll just ignore that a bit and just show a number of cycles and give the Bode plot. It is about experimentation. Just see how the Bode plot looks like and if this is what you want to have. So now you see that it starts from 1 kilohertz and the gain has increased to all the way to 60 dB. And I can keep doing it, but if you look to the data sheet of this this opamp, can we zoom that a bit in? So this is what we should expect. So if I would go to 1, 2, 3, 4 hertz, I would be able to go all the way to 105 dB. And around 10 hertz it should be. So this is very hard to measure, because the loop gain is so large that the output divided by the loop gain is a very small input signal at negative input. So on the second channel, that's basically the blue one, it will become an extremely small signal and it will be buried in the noise. So this lower part, I'm not really able to do that. But well, here at 1 kilohertz, I see that loop gain is, well, can I round it? I think about 60. So 1 kilohertz, it should be 60. And I think that, yeah, that is what this also tells. So this entire plot all the way, but you do see I now miss something here. So there is 100 kilohertz, 200, 300, 400 kilohertz. And that's also why I don't plot the phase margin, because I don't cross the 0 detection. And there is a way to change that. If I go to DHO-REMOTE, it's basically about this filtering. If I increase this to 70 dB, I might pick up more noise, but I might also go further, and I'll show you how that looks like. There you are. So now it does cross, but there is also a straight line here, and that's because there is also a point picked up at 20 megahertz. We're not interested at 20 megahertz. So what I prefer to do is just limit the output to 2 megahertz and do a capture again. I can also zoom in here, basically that would be the same, but well, I'll show you. So now the output is just going to 0, but this is sufficient for phase margin. So I can also zoom around this area. So around 727 kilohertz, the loop gain is 0, and the phase at that particular point is 72 degrees, and it's also plotted here, and I also plotted, I plotted here as well. So look at the command line as well. It's not really needed, but this gives some extra information. This is the lowest frequency bin, 31 hertz. So all these frequency points plotted here are separated by 32 hertz. That's the resolution. Yeah, basically this shows that. No, let's close some windows. This shows that with a little transformer that you can measure yourself with the same software and the same scope. And then you have an injection transformer. And this is, by the way, my breadboard setup, where here I have the opamp and all kind of long leads. So yeah, above 1 megahertz it is. It's probably not very accurate. So, but this is a quick setup where I put the transformer in the breadboard, and yeah, I just wired it up. Where do I have the schematic? Let's see. Oh yeah, here. So this is basically the setup what I make. Oh, there's one thing I want to show, that I can also make it unstable. So the op-amp might become stable if I put a capacitor at the output, and that would lower the phase margin. Now give me some time, then I'll plug in the capacitor. Okay, so that has been done. Now everything looks the same from this distance. And I plot again. This camera is disabled. Both plot. So now this capacitor of about 1 nanofarad is placed on the output. And this seems to be the same plot, but you can see that now the phase margin has dropped to 44 degrees. And actually that's what I consider to be not good anymore. Well, not good. It will all work, but it becomes a bit unstable. And you can also see that in the time domain. If I just zoom in a bit, then you can see what happens. So yeah, there is a step, but around the step there is also quite some ringing. And that's what happens as soon as the phase margin is not sufficient. Actually the ringing is a bit more, so I think the actual phase margin is lower than 44. And that might be because of noise. Let's zoom in around this part. So my software has said that the crossing is over here, but you can see that it is yeah, that is this tiny peak that goes below 0. But if you take the average of this curve, I think it is more fair to say that the crossing is over here. Right, so this is barely above 0, and that is shown by the lots of ringing. So I expect more a phase margin of a few degrees. So instead of here, I expect the proper reading should be here. And that's, well, below here you have you can read the value. The x-axis is the same. So the first couple of values is the phase. And that's, so here it is, I put it at 44. So 45, yeah, it's a bit more. But actually the phase margin is actually more like here. So yeah, you can see noise can, especially if it is very close to the 0 happening, like here, it can spoil the output. So do zoom in and make common sense of it. And also you can try out different options, like increasing the frequency. Currently I stimulate, you can see the count here with 1 kilohertz. I can increase that to 10 kilohertz again. Perhaps that helps. So the repetition rate does not change. It is just that well, let's just try. Okay, what you now see is that I try to get too much signal, and all kinds of errors are being made, and that's because I pushed this. So I basically I should put a filter in there. The wrong points are being taken. So going back to 60 dB, which I made a default, shows that it's already better. I'm going to zoom in because I still think this is not Yeah, just around this part. So now, like, make it 55 dB. Yeah, I think this is already better. So it is just crossing here. It is on the edge of being stable. This is, well, you can see it from the ringing as well. This is not stable. You don't want to have this. And now the phase margin is, yeah, 2 degrees. At least I made it deliberately unstable by placing a capacitor at the output of the op-amp. And by having this in the feedback loop, I can clearly show this in the Bode chart that this setup is uh, not stable anymore. So this shows the value of an impulse response on a linear control loop.